Good afternoon, everyone, and welcome to today's Earth and Environment Department. It is my pleasure to introduce our speaker, Dr. Landsea. Dr. Landsea is the branch chief of the Tropical Analysis and Forecast branch at NOAA's National Meteorology Center in Miami, where he leads efforts to produce wind and wave forecasts across the Atlantic and Eastern Pacific basins. His work plays a critical role in supporting hurricane forecasting operations and improving our understanding of tropical cyclones. He earned his PhD in atmospheric science from Colorado State University, where he worked with Dr. Bill Gray, a pioneer in hurricane research. Over the course of his career, Dr. Landsea has contributed extensively to the science of hurricanes with expertise in seasonal forecasting, climate variability, and reanalysis of the Atlantic hurricane database. Notably, his work has helped refine our understanding of historic storms, including the reclassification of Hurricane Andrew as a Category 5 advance. Dr. Landsea has also participated directly in hurricane research missions flying into the storms as part of NOAA's Hurricane Field Program, and has authored more than 60 peer-reviewed publications in leading scientific journals. His contribution has been recognized with numerous awards, including honors with the American Meteorological Society and the U.S. Department of Health. Today, he will be presenting a talk titled Opportunities to Apply Hurricane Research in the Midst of Hurricane Forecasting Operations, where he will share his insights from decades of experience research and clinical aspects. Please join me in welcoming Dr. Landsea.
Thanks, Alan, and thanks, Oscar, and thank Professor Cinto for inviting me today. It's an honor to be here and chat with students and faculty. My talk today is one that is kind of a little potpourri of activity. What are we doing now at the National Hurricane Center in my branch? And what are the three little studies that I've contributed to that have come out of operations? As I mentioned to Professor Cinto, we practice science every day. We don't do research, but we're using the science to provide products and services to the public. And so sometimes there's opportunities where we're like, well, why is it like this with the hurricane? Or why do waves do it like that? And so when you are making forecasts, sometimes there's things you don't understand, and it leads to some new hypotheses to test. So I wanted to share some of this with you. My name is Dr.Landsea, and I've been at the National Hurricane Center for 21 years on campus. So we're exactly a mile away on 117th Avenue. And before that, I was at the Hurricane Research Division on Virginia Key. So I've lived my life both as a researcher and a forecaster. And you might say, well, that can't possibly be, oh, what did I do there? All right. There we go. That can't possibly be your name. Right. If you did hurricanes and you lead a marine forecasting group, but yes, that is my real name. And when my wife and I were expecting our first kid, this is 25 years ago now, I thought I had the best name for this kid. And the nice thing was it would be pronounced the same way if it was a boy or a girl. And so if it was a girl, it would have been E-R-I-N. If it was a boy, it would have been A-A-R-O-N. Of course, that's pronounced air and Landsea. So we didn't do that. But instead, we have these three folks. So that's Mitchell, that's Elena, that's Frederick. It's a couple years old now. And those are retired hurricane names. So I convinced my wife to name our kids after destructive cyclones. Okay. So who's going into meteorology here? Me. All right. A couple of you. We're weird. We're really good. just let you know they're awesome. A little strange.
Professor Burke named his daughter after the Hadley settlement.
The Hadley settlement. Yes. He's got one up on me then. That's it. All right. So that's my real name. A little background on me. I did get a chance to fly on the Hurricane Hunters when I was at the NOAA lab, either the Orion P3s that go right into the center of the storm, as well as the Gulfstream 4 jet. And as usual, and this is 30 years ago now, 25 years ago, a very smug look. All right, I knew everything back then. All right, now I realize I don't know anything. Okay, you get older, you get a little wiser. And then 21 years ago, I switched over to the National Hurricane Center. And the first 12 years, I was the Science and Operations Officer. So if you want, what does a science officer do? It's like Spock, but with much better shirts and no pointy ears, okay? So it was my job to be the interface between academia and the forecasters. And that was really neat. And I got to learn forecasting. And the last 8 years now, I've been the branch chief of our 16 marine forecasters. So we do forecasting all year round of winds and waves and provide warnings for folks over the open ocean. So, so along the way, as I've been in this job, I've really had a chance to do a little bit of applied research along the way that stemmed out of our operations. So I'm going to talk about 3 little projects, but I did want to advertise what we do. And so we've got 2 main groups. We got the hurricane forecasters, real sexy part. We have the marine forecasters that do winds and waves. That's my group. And so to paraphrase our mission statement, we provide wind and wave forecasts and issue warnings over the Gulf, the Atlantic, the Caribbean, and the East Pacific. So 10 million square miles. So who do you think, I'm asking you a question, who do you think our customers are for these wind and wave forecasts? Just shout out an answer.
Shipping.
What's that? Surfers, that's a good guess.
Shipping.
Shipping, yes. Any other guesses? Yes.
Recreational boating.
Recreational boaters? Okay, so the real answer is our customers are the Mariners and the Mets. We've got a lot of baseball fans at the Hurricane Center. Maybe not those Mariners and Mets, but these Mariners and Mets. So it is the cruise ships, it's the cargo ships, it's the oil tankers, it's the oil platforms. It's the Navy and especially the US Coast Guard. And I'll talk a little bit more about the Coast Guard. It's the folks with the giant personal yachts. Does anybody have a giant personal yacht? I'm almost ready to retire. So if you do, I'll become your personal meteorologist. Nobody's got a giant personal yacht. Okay. So those are the Mariners. The Mets are the Caribbean meteorologists. So each country in the Caribbean, Central America, and Northern South America has their own weather service. And they're tailoring the forecast to folks in their country. We provide big picture information for them. So those are the customers, the Mariners and the Mets. Who do you think is a customer we don't want? Continuing the baseball analogy. Well, of course, it's pirates, okay? We don't want the pirates to be using our forecast. And the sad thing is there are real world pirates out there. Not as much in the Western Hemisphere, but in the Gulf of Guinea and Indonesia, there are pirates out there. And so we don't want them using our forecast, but they may be as well. So I do want to show a little bit about where we're making predictions, okay? And what the United States, we've got jurisdiction over the Northeast Pacific as well as the Atlantic. And currently, the way we break it down is geographically, that within 60 miles of the coast, that little pink ribbon, that is issued by the local weather forecast office. And so here on campus, we have the Miami Weather Forecast Office. And so they do from here out to Bimini, about 60 miles from the coast. Beyond that, we do the forecast for the rest of the Gulf, Caribbean, the Atlantic, all the way to 35 west longitude. North of Jacksonville is the Ocean Prediction Center. And similarly in the Pacific Ocean, it's divvied up by geography. So it looks small in this map, but it's 10 million square nautical miles. So it's a big chunk of ocean. We don't just forecast that during hurricane season, we do year round. So let me show an example of how we work with the hurricane forecasters. So as you may know, hurricane forecasters, they're also on campus here. They issue the 5-day cone. Some people call it the cone of death. Some call it the cone of uncertainty. If you're an emergency manager, you call it the cone of overtime because you're going to be working a lot of hours. But an hour before that goes to the public, it's sent internally throughout the weather service. And in this case, this is Hurricane Ida as it was heading up to Louisiana. And 1 hour before it goes public, we're all building that forecast in to our predictions. So the cone is kind of a big, broad picture. We're filling in the details. So that pink star represents 1 day forecast, and we're providing all this. We're providing a gridded forecast of 10-kilometer resolution, 3-hourly temporal resolution of winds and waves. So the mariners over the open ocean can get an idea of what. We do that right now deterministically, but we're moving to more probabilistic guidance for mariners in the future. And so this is done every 6 hours. We have tools that we can use to build this vortex into our predictions and adjust it every 6 hours to make sure it's consistent. Because we wouldn't want the Hurricane Center saying, oh, it's going to be a category 4, but we're only saying 6-foot seas. It's got to be more like 36-foot seas. All right, so that consistency is important for messaging, because if people hear contradictory information, they don't take action. Sometimes you don't want them to take action, but sometimes you do need them to start doing something. So when we're doing our forecasts, we have a gridded database of winds and waves and warnings, and we use that database to populate our products. And some of that are the text products that nobody reads anymore, right? Because nobody wants to read. Everyone wants the video or graphics. We understand that. We have graphics that for decades we've been sending out by radio technology, but now there's Starlink. And so nobody's using radio technology anymore. So we're having to catch up. And the grids themselves are accessible. So the nice thing is we're building in more automation to allow our forecasters to look at the meteorology and oceanography more, and also for us to provide more products and services. So let me show an example of a success. And this was from Hurricane Milton a 1.5 years ago. And as you may recall, it formed in the Southwest Gulf. I'm required by law to call it Gulf of America. You could call it Gulf of Mexico, I don't care. But it formed in the Southwest Gulf, and it started heading toward Florida. Each of these triangles is a ship. You can go onto a website called marinetraffic.com, and every large ship is required by international law to have a satellite transponder. So if they start getting into trouble, they push the button, and the local Coast Guard goes and helps. So you can actually see all these, unless you're a ship that doesn't want to be seen because you're smuggling something. All right, and so you can see there's lots of ships out, and in those boxes there's dozens of ships. And these aren't recreational boaters; these are the big boy boats, the cargo ships, the oil tankers, the cruise ships, the fishing vessels. And you can see the next day it became a hurricane. So the green is tropical storm winds, the orange is hurricane winds. And what was interesting is to see the response of the mariners. What are they doing? Because the next day, as the hurricane is forecast to hit Tampa, now the Gulf, the Eastern Gulf is vacant. The ships are getting out of the way. So they're seeing the forecast, they're responding to staying safe. And I don't know if they're using our forecasts, if they had a ship routing company, or they're doing their own forecasting, but they were doing the right thing. So a day before landfall, there's not a single ship over the Eastern Gulf of Mexico. It's amazing. That's wonderful. Doesn't always happen, but it did in this case. And what was even more incredible was the forecast was it for not only to be strong when it made landfall, but to also get really big. So when it made landfall, it looked like this. You had tropical storm winds all the way from Flamingo to Apalachicola, and yet, despite that gigantic size, 0 ships over the open ocean. That's wonderful. Doesn't always happen. All right, and it requires a human to make those decisions to stay out of the way. But that's gratifying to us. So one thing I mentioned, one of our customers is the US Coast Guard. So unlike the US Navy or the US Air Force or even the Marine Corps, the US Coast Guard has exactly 0 forecasters. They don't have any meteorologists in the US Coast Guard. And they're fairly small compared to the other armed forces. And so by design, Every 10 years, the head of the Weather Service and the head of the Coast Guard re-sign a MOA, memorandum of agreement, where they help us communicate with the mariners and we help them with decision support. So what does decision support mean? Well, one is we provide them specialized spot weather forecasts. And so this shows last year we did 55 of these spot forecasts over the Gulf, over the Caribbean, over the West Atlantic. And it could be for a ship in distress. It could be for an aircraft that's ditched. It could be for an oil spill. I mean, Deepwater Horizon. I think most of you all remember that still. It could be for law enforcement activities where they're chasing the bad guys. Or it could be for man overboard. And did you know, 90% of the time, when you hear the term man overboard, it is actually a dude overboard and not a woman. Any guesses why when you hear man overboard, 90% of the times it's a guy? Any guesses?
Because they dominate that industry and might not specifically more likely to be risk takers.
Yes and yes. Yes, so sometimes they do stupid things on cruise ships and get in trouble. But the main reason is that cargo ships, oil platforms are dominated. 85% of workers on those are men. And it's a risky profession. So exactly right. Dumb things get guys in, but also riskier professors. One thing we provide for that, this is kind of more on the oceanography side, is sea surface temperature. Why would the Coast Guard care about sea surface temperature for a man overboard? Right. There's an equation. How long will you live depending on how cold the water is? And even if it's 80 degrees, you only got about a day. So it's a very sobering fact, and they're looking for something. We also amp up our support during hurricane season because the Coast Guard, one of the responsibilities, and this is a big economic one, is there is a captain of the port. And he or she has to decide for Port of Miami, Port of Everglades, all the ports in the United States, which ones to close and when. You don't want them closing too early because all those shipping interests will be pissed off at why is it closed and it's a pretty day out, but you don't want to close too late and get in trouble when a hurricane comes. They also have to decide for their own assets because most of the Coast Guard is actually on the coast. Do they stay in business or do they board up and evacuate? And they've got to get their cutters and their small boats and their helicopters and their fixed wing aircraft out of the way of the hurricane, but not too far away, because sometimes they are first responders. And just 4 years ago now, 3.5 years ago, just the US Coast Guard, not even including the local law enforcement, saved 1,007 men, women, and children around Fort Myers. If you ain't from Florida, Fort Myers is that way 100 miles, not very far away, okay? Think about that, 1,007 people. That's even more that's in this classroom right now. All right, so it's amazing what they do. The men and women of the Coast Guard, it's an amazing mission that they have, and we're honored to help them out. Okay, so one other decision support service that we provide is in the Caribbean. Let me make sure if I can say this correctly now. Porque los especialistas en huracanes están muy inteligentes, pero no hablan en español. So we got some really smart practicing it. I'm not better. So we got some brilliant 11 hurricane forecasters. None of them speak Spanish. But of my 16 forecasters, half are bilingual, not me. And so they do the coordination calls with other countries. So for example, when Mexico is threatened by a hurricane, we make big picture forecasts, and it's one of my forecasters that coordinates to make sure that they understand the forecast is what does that country's weather service want for warnings. We also do Spanish language media interviews. And of course, with Telemundo and Univision here in Miami, good opportunities for reaching out to the public that way. And I also point out, Sandy Delgado, FIU graduate, 8 years ago. All right, he's a really great guy. Got his master's. So just to wrap up about what we do on day to day, It used to be radio was the way to transmit information out way over the open ocean. Radio graphics, radio text, and radio voice broadcasts. But now they have this thing called Starlink, where SpaceX is launching all these mini satellites. And it's a good thing for the mariner because they get high-speed internet, reliable anywhere. And so they ain't looking at our one graphic anymore. They're looking at like predict wind or windy.com, some beautiful graphics and video. So we're trying to keep up with them. And what we're doing is we're providing new products that are all digital so they can use that to stay safe. And an example, this is a polygon that's accessible as a KML file, and you can overlay it on your navigation software. It's essentially a no-go zone because you have tropical storm winds, 50 knots, and then red would be hurricane force. And so this is where we're trying to make sure that as mariners get high-speed internet, they use our official products to stay safe. Okay, I think I'll stop on that part. It's a little bit about our mission as marine forecasters. Any questions or comments before we move on? Yes.
I do have a few, just related to the last thing you commented on. Industry-wide in shipping and in weather, is radio instrumentation being maintained as a backup to Starlink? Or are we everybody's just full bore ahead on satellite?
Yeah. So the mariners are not required to have the radio technology anymore. They are required to have a satellite phone that they've had for the last 15 years. It's real expensive to get information that way. But as Starlink has proven to be very reliable and cheap and accessible anywhere, they're turning off their radio stuff. And so we're realizing that and pivoting toward all digital. So, and it's a good thing. It's a good thing with the mariner. So I don't blame them. So as I mentioned, since I've been at the Hurricane Center in 21 years, I've had a chance to do a little bit of applied research where things come up in operations on the hurricane side, like, why is it like that? Or how can we do it better? And so I've published a few of those. I wanted to talk about 3 small projects in general. And the first of which was from a Pathways student intern from the University of South Alabama. And for those that like the opportunity to work at a government lab, the Pathways program is a really good one, especially for undergrads to get a chance to work at a government lab for the summer. And Sam worked with me a few years ago, and we were looking at, well, how fast can hurricanes spin up? 70% of the time in the Atlantic and 95% of the time in the Pacific, we don't have hurricane numbers. We don't. There's just that not very many planes, and sometimes the storm's too far from land. And so we're using satellites. And the technique that we use to diagnose how strong a hurricane is a pattern recognition technique called Dvorak, where you're looking at the curvature of the deep convection thunderstorms and relaying that to other storms in the past. Right now, we have a mix of subjective human-derived and AI versions. My guess is the AI version is going to surpass what we do, but it ain't there yet. And so one of the aspects that this Dvorak technique has is you come up with a number and it relates to a wind speed. So for example, if it's a Dvorak 7.0, it's about 160 miles per hour. But what we've seen and what Vern Dvorak, in Genius 50 years ago, he realized sometimes the convective pattern can look like it's developing very fast, but in reality, the dynamics, the wind flow doesn't respond instantaneously. And so he built in what are called constraints, where what looks like to be something really strong, he puts a lid on. And so one example is for these current intensity numbers at 24 hours, the current constraint back then was it could only go up 2.5, which is about 50 knots, 2 categories. But what we've seen is that sometimes storms spin up faster than that when we measure them by aircraft. And so an example, Hurricane Felix on one day was 65 knot category 1 hurricane, and then just 18 hours later it was a category 4. And we know it was because we had a hurricane hunter in there actually measuring the winds. But again, we don't have the hurricane hunters all the time. We want to calibrate these satellite techniques properly. So we decided to go back in and say, well, how can we adjust, or should we adjust this Dvorak technique to make it more accurate? And so we looked at all the cases where we had hurricane hunters and storms that spun up fast. So we had about a 20-year database where our hypothesis was, can we adjust the Dvorak to allow for stronger storms? We thought we could, but we didn't know. And so we put together a database, and if we're able to be successful with it, then we could improve this technique for estimating how strong storms are. I'm not going to go into the details, but it's important for testing a hypothesis that you build a big database, and you very clearly look at the errors in the approaches, and we're trying to minimize the errors, maximize the correlation, minimize the bias. All right. And so we looked at how well different constraints work. And so we just said no constraints. If it says it's 150 knot, category 5, that's what it is. Well, that didn't work too well because you ended up with right. So that's the low bias. There wasn't any bias there, but the errors were higher. So root mean square error was higher, and the correlation was a little lower. The current constraint was pretty good, had a large correlation, but what we found is we loosened up the constraints a little bit, allowed for slightly stronger storms to occur from the estimation that our correlation was a bit higher. The bias was still pretty low, and both the absolute error and the root mean square error were the lowest. So we kind of found that sweet spot of low bias, high correlation, and low root mean square error. And so we were able to adjust these constraints to some degree to loosen them up. So we changed those at an 18-hour and a 24-hour change over time to allow more intensification. And so previously the highest wind speed increase that was allowed in a 24-hour period was 68 knots. And now we allow 80 knots. And this actually has an effect on the climate records, because now our climate records are going to allow for stronger storms when they're just estimated by satellite. So it's an example of where changes in policy and changes of physical understanding can alter a database in a bad way. That's just an aside. So it was nice to see this work applied, where we did a hypothesis, collected a database, and tested different approaches. So we were able to add that in. So that's first one. How strong can hurricanes get? How fast can they spin up? The second one was some discussions we had out in the hallway with myself and John Cangialosi, who's one of the senior hurricane specialists, back in 2018, when we were looking at our forecast track, errors in knowing where a hurricane's going to go. And when we started looking at the errors, and so this is a 1-day forecast, 2-day, 3-day forecast, and a 5-day forecast. And the days 1 and 3 go back to 1990. We started doing a 5-day forecast back in 2001. And you can see the errors have been dropping dramatically. That's great. All right, we're getting a lot better now than we were back in 1990. And it's not because we have a bunch of Einsteins now, we had a bunch of knuckleheads back then. It's because the computer models are so much better, and the satellites are feeding the computer models for the data simulation. And in fact, this is, to me, so stupendous in its accomplishment. One of my colleagues said that this massive improvement in hurricane track prediction in one generation is the greatest accomplishment in the history of numerical weather prediction. So it's great because you can have a smaller cone, smaller warning area, less overwarning. It's all good. But if you look at the forecast, if you look at the errors, they've been going down, and you could just extrapolate. It's going to get to 0 in 2030, right? The errors go to 0. right? Just linear extrapolation. We're gonna have no errors in 4 more years. Well, when you start looking at it a little more, instead of a linear best fit, if you just use a 5-year standard mean, it's like, well, it was really steep here, and it's kind of plateauing. Huh. And if you just look again at the last 5 years of this cycle, yeah, there's some improvements, but it's a pretty noisy, and it doesn't look like it's been continuing. And there's another way to look at the errors too. Instead of the actual errors, you can do a skill diagram. Compare your errors versus a benchmark model called climatology and persistence. So if you improve over a benchmark, you're showing skill. So the higher, the better. And in this case, skill's been going up from 1990 onward, but in the last 5 years, at least from this time point, from 2012 to 2016, the skill plateaued. So it looks like the errors were starting to plateau and the skill was plateauing. We're saying, huh, does that mean getting near the limits of predictability? And there had at that time only been a couple of studies looking at theoretically what are the limits of predictability. And if you know back to the time of Lorentz, you know, he was the one that came up with chaos. And the idea is errors in the initial conditions lead to big errors later on, meaning there's never going to be perfect forecasts. Never, never, ever. So there are limits to be reached. And so there was a couple of studies where we could estimate what those errors are. And from those, it looked like, from those rough calculations, that we were getting close to the limits of predictability for 1 day, 3 days, and 5 days, just from those 2 simple theoretical studies. So that made us say, oh, maybe we are getting close there. And so we published it, and just some of the things were, you know, maybe we're reaching the limit of predictability where we get a little better, but we're kind of plateauing, and that we need to convey this to our users, the emergency managers, the media, and the general public that, hey, it's not going to get any better. This is as good as the science is going to let us do. And then instead, we can focus on improving forecasting, winds, structure, and other impacts. So that was 8 years ago. And so now we can take a look. Do we really reach a plateau? And so now we can add in 8 more hurricane seasons. And so when we do that, here's that day one, and yellow's the day 3, and blue is the day 5. It sure looks like the improvement's slowing down or is stagnating. And again, if you go back, those are the linear trends through 2012, and extending them down, the errors are a lot higher than that linear trend would have suggested. And again, just looking at these 2017 to 2024, that's a flat line. That's a little lower, decreasing with time. That's flat. So the errors really had not gotten any lower. Sure looks like you've had this massive improvement, decreasing errors, and then the last really about 10 years, no changes. Now AI has arrived, right? AI is going to solve everything. Well, this last year was the first hurricane season we started having AI models. We had Google DeepMind was working with our forecasters to get those new techniques in, and they were the best model. But did it improve our bottom line? And it's right on the edge there. But there's the 5-day forecast here saying, there's the 3-day forecast saying, there's the 1 day. Not getting any better. So I still believe we are at the point where no matter what the technological improvements, we're not going to get substantially better ever for track forecasting. I think we're there. All right. And so we have to realize that there's always going to be uncertainties and errors and move forward on that. But it's still an open question. The question is, what is the limit for track prediction? And I think we may be there based on the last decade of trackers. All right, last little story. So I've worked some with our colleagues at NOAA Research out of Virginia Key. and in particular, Jason Sipple and Sarah Ditchek and Kelly Ryan. And one resource that we have when a hurricane is happening are these hurricane hunters. And one is the Gulfstream 4 jet. It doesn't fly through the hurricane, it flies around. And the idea is it monitors the environment. And it's got a radar, tail Doppler radar, and it has drop zones, instruments that it launches. So the idea in the past is launch in the environment and launch in a circle around. And that circle is usually about 300 kilometers from the center, but not go near the center. All right, it was a little more dangerous with this jet. These drop zones cost $700 each. We use them once, we never see them again. Okay, so it's got winds, it's got pressure, it's got temperature, humidity. We don't see them, we just use them once. And so these missions cost about 30 grand every time we task the Gulfstream 4 to help us with the predictions. And in the past, when they fly, it helped the forecast by about 20–25%. So it's very useful in flying this aircraft, dropping these sondes to improve the forecast. But we were wondering, we spend 30 grand every day during the season to fly this. Are we doing the right thing? How can we best utilize this amazing resource? Are we doing the best we can with it? And there had been a couple of experiments. And so one of the experiments was a NASA one where they had a global hawk flying in the stratosphere. And they were able to sample with mini drop zones and really saturate the storm. There were also some observing system experiments where you take a subset of those extra observations and see, well, what happens when you take some out and include others. And there was also use of the NASA DC-8 as well in the Shout experiment. And so the combination of these started to suggest that the drops, the measurements near the storm were more important. So we're like, can we change how we fly into the hurricane to improve the forecast? And so we did what's called an observing system simulation experiment, or OSSE. This is just completely hypothetical, but we've got hypothetical flights around the storm. And in this case, we're like, well, what if we've got a 300-kilometer ring? And what if we have a 150-kilometer two concentric rings, where we get a little closer to the hurricane and dropping sondes near the middle? And it turns out in this simulation, and when you did this double ring and had extra observations near the hurricane center, you had the lowest track errors. The errors were decreased by about another 10–20%. Not massive, but an improvement, especially in an area where it's harder to improve the forecast. And so what we did, we designed a double circumnavigation where they fly an inner ring and an outer ring to better sample the near storm, or the outer part of the vortex. So when you do that, and you can only fly 9 hours total, you got to track some ads. So instead of more environmental observations, we're putting more near the middle. And so that's been successful. This is an example of what we did, where we took what we were going to do, and the red ones are the drops we got rid of because we can't fly more than the gas allows us. And the green ones are where we added some in the middle. We first used this in Hurricane Florence in 2018, and two-thirds of the flights since have been using this double circumnavigation. And so we've been using it a lot. And it's nice because now we can take a look, has it actually helped? We thought it would. We did simulation experiments that showed it should work, but did it actually work? And so Jason and Ryan took all the measurements. In this case, one of the measurements into Hurricane Ian, was in the Pacific, in the Caribbean. Each of those numbers was a drop sonde, and there's, you can see that double circumnavigation. And you also have the tail Doppler radar. When you're at 300 kilometers, you don't see anything with the radar. You're too far away from the hurricane. But when you're at 150 kilometers, you're pretty close to the thunderstorms. So the tail Doppler radar actually sees them. So that's an example of with that double circumnavigation, you actually can get depictions of the convection. And so we did an experiment then where we ran one of the hurricane models with the dropsondes and then without the dropsondes. Yeah, and said, did this have an effect? Our hypothesis was, yes, this is improving the forecast. And we're spending a little more money to do it. Is it worth it? And these graphs, we look at the track errors, the peak wind errors, and the lowest pressure errors. And the red is without the drops near the center, and the green are with the drops near the center. And the track improves a little noisy the first couple forecast time intervals, but in general, the track was improved by about 5%, so slightly smaller position errors, but the intensity, the peak winds were systematically improved, and the lowest pressure was systematically improved. So the idea is that these extra measurements, these dropsondes, give us a better depiction of the structure, the outer core structure of the hurricane, and so that helps the model in its data assimilation and start. And so it looks like it was a good idea to spend your taxpayer money and launching some extra sondes near the center. And this all happens because we're in a room together and having lunch and chatting. And, hey, well, how's it going with the global hawk today? What's going on? And so don't discount the opportunity for interacting with other students, faculty, other researchers, and discussing with them. And you have a unique department because it's so multifaceted that you may get insights from somebody who's not a meteorologist, maybe he's a hydrologist. And so this was a fun project for us to implement and to see that it actually helped out. So for me, even though I've been in forecasting for 21 years, I still see myself as more of a researcher. And to me, this was kind of a neat laboratory where we got, what are the issues we're grappling with? Can we test some of them? So that's been a fun opportunity to try to do a little bit of research in an environment where we do forecasting. So I think I'll stop there and see if you all have any questions.